Okay, so we're going to be talking about types of forces. There's so many types of forces, but for the purpose of a mechanics course, there's actually maybe a good handful, like 7 or 8. Just so this video is actually going to explain all the types of forces that are usually in a mechanics course. So this will help us a lot with most of the bulk of this unit, which is free body diagrams and using Newton's laws to solve problems. So it's always helpful to know these types of forces, especially when you go ahead into the later sections of this unit. So I'm going to actually list a bunch, kind of like a catalog. I'm briefly going to introduce them and the idea behind them, but I'm not really going to go in too much detail about them because I have other videos for these specific types of forces. For example, like drag and air resistance, I'm going to hold it off until the very end, but some of them I'm actually going to introduce pretty more detailed than the others. So let's begin. The very first one is denoted like this. This is known as the gravitational force. And basically what it does is that it depends on a couple things. It depends on your mass, and it depends on whatever g is, right? We learned what g is in the last unit. On Earth it is 9.81 meters per second squared, so this is like an acceleration, if you want to think of it like that. G is an acceleration, and it depends on the mass, so it also, the whole thing depends on both these quantities. In fact, we actually give it a name in English. It's called weight. And a lot of people confuse weight and mass together, so here's a good, scenario to try to differentiate between them. So let me just draw it here. Mass is actually just an amount of matter. So it doesn't matter what location you're in, you still have the same amount of matter. You don't suddenly lose it if you're on the moon or somewhere else in the universe. You actually have just the same amount of matter all the time, so you have the same mass. However, weight is actually depends on gravity, right? So on Earth it's 9.81 meters per second squared, but on the moon it's a little bit less. So you actually have a different weight on the moon than you do on Earth, but you have the same mass on Earth as you do on the moon. That's just because of whatever g is on that planet or body you're on. And we'll talk about more about g and the gravitational force in the gravitation unit, but this is more just an introduction. So now the way I like to notate weight or the gravitational force is actually with an equation. So the equation that we use is the weight, or I'll write it as the gravitational force, is equal to the mass times the gravitational constant. So on Earth, I'll say it again, it's 9.81 meters per second squared. So the way I actually just notate it on what you call a free body diagram is like this. So let's say I have a person here, and he's just falling through the air. Its gravitational force always points down. So actually, let me just draw it at his center. Let's say right here. The gravitational force points directly down, no matter what, for the purpose of this, this unit. So it depends on two things. So whatever mass it is. So let's say I don't know how much. Let's say 50 kilograms. I'll just say 50 kilograms. I don't know how much that is in pounds. And on Earth is 9.81. So we just simply multiply these two, and we get the weight of the person, right? On the moon, let's say, or like on a different body of the universe, let's say the acceleration is actually, let's say it's 2 meters per second. So it's a small body that's still kind of large comparative to us, but not towards the Earth. Its gravitational constant is 2. So this guy's weight is actually 100 newtons, while on Earth it's going to be much more, probably around 5 times as much more weight. So that's the idea of the gravitational force. So we're going to move on to the next one, kind of like the counter for gravity. It's called the normal force. This is kind of like a supporting force. So it kind of supports something so that you don't keep endlessly falling forever, right? When we're standing on a ground, there's actually forces pushing us back up, right? We're not going to keep falling down for a specific reason, and that's because of the normal force. So if I were to draw the normal force, it would be at the point of contact, and it's just going to be pointing up, while my gravity is pointing me down. So they kind of cancel each other out in that sense, because if the normal force weren't there, we're going to actually just keep going down even past this ground. And the reason why there is a normal force is actually because of electrostatic forces between our feet and the ground, right? There's like microscopically, there's repelling forces that actually keep us standing on the ground. So that's the idea of the normal force. And the other point I want to make is, let's say I have this box on the ground. The normal force we know is going to point up, but it's going to point normal to the surface, right? Normal means perpendicular, so it's going to be perpendicular to the surface. Let's say I draw it here now. It's going to be perpendicular to that surface here, right? Making that right angle. And same thing here. If I push it along a wall, like let's say I'm pushing it with my hands like this, the normal force is actually going to point perpendicular like that. So that's something you have to keep in mind, especially throughout this unit set. The normal force is a supporting force that points perpendicular to the surface it lies on. And then the way we notate it here is force subscript n. The way I do it, so it's very similar, is just whatever the subscript is. I'm just going to write that as the normal force, and we'll see how to use the normal force in a future video. Next one we want to talk about is tension. And tension is associated with any type of rope or cord or any type of rope or cord or string, any type of that. Anything that falls along those things. And we can see tension all the time, right? When I'm pulling something with a string, that's this force right here. I'm going to write it in orange, is the tension force. And say it is actually moving this way along the ground. And then we can also see tension force if I hang something on the ceiling. Like for example, let's say we have a hanging lamp, for example. I don't know how to draw a lamp. There's tension force right here. It's keeping it attached to the wall, so it's actually going to be pointing up. And then there's gravity, right? So they balance each other out in that sense. So let me actually draw that more clearly here. If I were to have a lamp here, we have the tension force pointing up, but then we have its gravity canceling each other out, right? So that's the idea of tension. And it's also associated with a lot of pulleys, right? I'm just going to draw this as a pulley, and let's say you have it like this, and then I have two blocks located on it. There's tension here because the blocks are kind of pulling on each other in its own way. And the job of the pulley is just to redirect redirect what the tension force is pointing at. So let me draw a better example just to show you. Let's say it's attached to this table, and I have this other block here. So the pulley acts as basically a redirector. It redirects the force to a different direction. So now it's horizontal compared to vertical. And then, like always, the way people like to notate is like this. The way I like to notate it is like this, the subscript, right? Keeping that same convention. And then we're moving on to the next one, which is friction. Friction is a very complicated one. A lot of people don't like working with friction, especially in physics problems, for a very specific reason, is that it's just complicated. It's a resisting force, right? It resists motion. So I'll write that here. So let's say I'm on the road and I just start driving, and I just there's a friction force that's making me a lot slower than I actually should be going, and that's the idea of friction. Another thing is that friction actually helps us walk, because without friction our feet are just going to be sliding on the ground, kind of like on ice, if you want to think of like that. Ice has it gets to almost no more friction, right? So just imagine yourself walking on ice compared to walking around on a road, right? It's easier to walk on the road than slippery ice because of there's more friction between your feet and the road than the ice. And it actually, friction helps you the walk, right? I showed that in the last video with Newton's third law. So imagine that friction force being not there. It's not going to help you propel yourself forward. There's actually two types of frictions. There's kinetic and there's static. So kinetic's associated with motion, right? Associated with motion, while static is not associated with motion. So I'm just gonna just pretend that was in the quotations. So the way we notate this, like always, is capital F, and then you usually put subscript F, but then we have to distinguish which type of these. So if it's kinetic, you put a K, or you put S. And then again, we have to, I'm going to show my notation, so my notation is just a subscript. And I feel like this is much easier to write than writing a bunch of subscripts within subscripts. Now what can we talk about? We can talk about the idea. The idea is that friction is actually related to the normal force. So I'm going to draw this kind of helpful thing. It's not really the true equation. It's just that it's related to the normal force in this way. It's kind of proportional to the normal force, meaning that this is a constant that kind of scales it in a way, if you want to think of it like that. It's related to the normal force, and this is kind of the thing I like to remember, but this is not really the true equation. There's actually kind of more technical details, kind of like depending on what type of friction force, it's a static one, so it can only be like specifically less than or equal to this times this, and we're only talking about size. So I'm not really gonna show that. I feel like this one's a little bit better to remember, is that just the friction force is equal to a coefficient or a constant, which you call the coefficient of friction, times this normal force. And the key takeaway here is just that the friction force relates directly to the normal force, and we'll talk about friction force a lot in a different video. And then we're going to go to our final force. This is air resistance, otherwise known as drag. People like using drag a little bit better. And this is another resisting force that opposes motion. So let me write it like this. Opposes motion. And the way I like to think of drag is this: picture yourself skydiving, and on Earth there's actually a lot of like air particles, right, that's kind of like in your way. And basically what these air particles do is they kind of block your way, so you have to push them out of the way, so it kind of slows you down in that regard. And we're just getting the idea of air resistance or drag, and in one of the last videos of this unit I'm going to go into technical detail about air resistance and drag. And the way they notate it is like this, and the way I notate it is like this. We're going to be talking about this again in a future video because this involves a lot of calculus, especially because the idea of a resisting force involves a lot of calculus, specifically this one. Friction not so much because we have a relation, but this one actually depends on several things. The idea is that the drag force depends on how fast you're going through it, so your velocity. It depends